For part 3 of Organic Chapter 16, we're going to discuss some other nucleophiles that we can see reacting with aldehydes and ketones. We'll start by discussing amines acting as a nucleophile. In 16.8, we'll discuss a variety of nitrogen nucleophiles and what they form. And then in 16.9, we'll talk about oxygen nucleophiles. The revolving theme throughout this section is the fact that these nucleophiles now have a lone pair that remains on the attacking atom after they've served their purpose as a nucleophile, and that changes some of the reactivity that we see. And so let's take a look at amines and what they can do. An aldehyde or a ketone can react with a primary amine to form what's known as an imine. That's what's shown over here on the right. An imine, that's something that contains a carbon-nitrogen double bond. Okay, so you see that C double bond N, and then you've got an extra alkyl group over here. Here we've got an ethyl, over here a benzyl altogether. Right? You see C double bond N with an extra alkyl group. That's called an imine. Okay. And these imines have synthetic utility. We'll see that in a couple slides. Yeah, they have the same hybridizations as what we would expect with a carbonyl, okay, similar reactivity. And there are also some types of derivatives that we can see, right? But right now, what you want to know, aldehyde or ketone, primary amine, that forms an imine. Okay. We also do see some derivatives, as I just mentioned, okay? These derivatives are the so-called derivatives, not specifically imines, because notice now, while there's still a C double bond N, there's not an alkyl group over here, right? I wouldn't call that an R group, that NH2. Okay, so anything else, if it's not an alkyl group, it's called an imine derivative. Okay, so just be aware that those exist. I won't specifically be testing any imine derivatives in 2540. But we should be familiar with the mechanism of how these things are formed. And it's done, like we've seen in the previous videos from chapter 16, by a nucleophilic addition elimination. We see those a lot with aldehydes and ketones. All right, the first step, we're looking at a ketone here, is my amine is adding to the carbonyl, right, acting as a nucleophile. I've formed an alkoxide here, okay, which is going to pick up a proton in solution. That then forms this protonated group over here. I've got my protonated nitrogen next to that OH, right? That's called a carbonylamine. It's protonated, right? I want to deprotonate it then to form the stable, well, more stable, it's not perfectly stable, tetrahedral intermediate. That's known as just a carbonylamine. Okay, so protonated, then I deprotonate it. Okay. Now I've got an equilibrium going on here, right? Because I could have protonated my nitrogen there. I can protonate my oxygen and move down here, right? So I've got an equilibrium that's going on there. Okay, but if I protonate the OH, and now I have water acting as a leaving group, then my lone pair that's on nitrogen can shift down, right? Form a double bond that's going to end up in my imine there, kick off water. Okay. Now I've formed what's known as a protonated imine, and then the final step is just to have a base come in, pull off the proton, and then I've formed my final product, the imine. Yep. And I can push this reaction to completion, thinking about Le Chatelier's principle, by just removing this H2O, right? This water that's formed at the end, if I remove water as it's formed, it drives that reaction to the end, favors the formation of my imine. A final product of a ketone or an aldehyde plus a primary amine. Okay. What's going on with some of these intermediates? Okay. Over here, I've just got an OH. Okay? And we talked about those in previous videos. They're stable. Okay? But with that protonated water, right? Now that's not stable. It's not going to stay there, even though these could exist in an acidic solution because there's nothing around to boot them off as long as there's no nucleophiles in solution. Here, as soon as I protonate that water, I have a lone pair that's just chomping at the bit, right, waiting to shift down and form a double bond there. Okay. So you've got a couple of considerations, but that's the theme here in this section, right? That lone pair that still exists on a nucleophile. Another thing to look at for the formation of amines is you do have to be careful with the pH of the solution. Okay, this graph over here is called a pH rate profile. And with so many different things going on in solution, right, it requires an acid catalyst for some of those protonation steps that we just talked about. Okay, so we have to have an acidic solution, but yet we have to worry about protonating the primary amine itself, right? Because if I get too acidic, the lone pair on that nitrogen is going to pick up a proton, and then it doesn't have the ability to act as a nucleophile as well. Okay, so there's a lot of information on this slide, but this is the key takeaway right there in the middle. Okay, whatever the pKa of your amine is that's acting as your nucleophile, the ideal pH for your amine formation, 1.5 less than that, right? So pKa is 6, you would run it at 4.5. pKa of 10.5, you would run it at 9, right? 1.5, that's the golden number. These amines can also be hydrolyzed back to the ketone. Right, here we've got acid-catalyzed hydrolysis. We've talked about these already. That takes the amine and converts it back to the amine. It's protonated here in this situation and back to the ketone. Okay, now notice this is an irreversible reaction. It's only going in the forward direction because when this guy's protonated, we just talked about that, then it's not acting as a nucleophile. Right? And this is an important reaction in biological systems in the human body and everybody, really, right? It's a big factor in the stability of DNA. So how about secondary amines? Okay. In that situation, I can have a secondary amine react with an aldehyde or a ketone to form what's known as an enamine. Okay. So in this situation, an enamine is a tertiary amine, right? 3 alkyl groups on nitrogen, 1, 2, 3, 1, 2, 3, but it's an alpha beta unsaturated tertiary amine. So I look at my amine, right? Alpha carbon, beta carbon, there's a double bond between those, it's alpha beta unsaturated. And that alkene came from the ketone itself, right? Not from the amine. Notice it didn't exist here before. And this is another reaction that requires trace acid, right, but that's another one to have committed to memory. Ketone, secondary amine, forms an enamine, right? And it's also kind of hinted right there in the name, right? En from alkene, amine for the amine. How are these formed? Well, the steps are exactly the same. Okay. The only thing that's different is the final step here to form the neutral product at the end. Okay, now my deprotonation comes from the alpha carbon, or sorry, the beta carbon. Right? In this situation, my base comes in, plucks the hydrogen here, right? Those pair of electrons shift down to form the alkene. That's what's making the pi bond. This pi bond breaks and goes back to reform the lone pair on nitrogen. Yep, that's how we get the stable molecule. And just like amines, enamines can be hydrolyzed back to the ketone and the amine that they came from. We just, again, in an irreversible reaction, end up with a protonated amine. So what's the use of these amines in particular? They have good synthetic utility in that we can take a ketone or an aldehyde and then convert it to an amine. This is called a reductive amination. Okay? Reductive amination. That's where we take an aldehyde or a ketone, react it, in this case with excess ammonia, and it's done in the presence of a reducing agent, which is useful because this double bond that's in the amine is reduced faster than trying to go and attack the CO double bond directly. And so here we've taken the ketone, converted this carbonyl down over to an amine. And so there's a little bit of synthetic utility. See it here, and we see more of it here. The only thing to look out for, right, here's another reducing agent. We talked about a lot of those in the second video, sodium cyano borohydride. And that's a common reducing agent for these reductive amination reactions. Yep. Something that's commonly seen in the body with antidepressants. And that wraps up our discussion of nitrogen. I'm going to shift over and talk about oxygen next in 16.9. Yep. Now, the addition of water to an aldehyde or a ketone produces what we've already seen before in organic 1, a geminal diol, right? Remember, geminal means same carbon. Okay, we also learned vicinal right? Neighboring carbons. Here we've got a geminal diol. Textbook discusses it as being a hydrate, right? The addition of water to an aldehyde or a ketone requires an acid catalyst, produces a hydrate, which your text defines as a molecule with two OH groups bonded to the same carbon. Okay, so hydrate, geminal diol, synonyms, same thing. What's that mechanism looking like? Why do we need the acid catalyst? Well, to protonate our carbonyl in the first place, because water is a poor nucleophile. So we have to protonate our carbonyl first. Then when we've done that, we're allowing water to act as a nucleophile, deprotonate in the end, and then we're in business. We formed our hydrate. But the substituents that we're starting with are important. We do have to pay attention to the ketone or the aldehyde because they'll control the reactivity. Look at these numbers, right? Acetone doesn't easily hydrolyze. That's why we use it as a lab reagent all the time. Okay, only 0.2%. Versus formaldehyde, which is going 99.9% to the hydrate. So why is that, right? Why do these substituents on either side of that carbonyl group have such a big effect? Well, it's for two reasons, right? These alkyl groups, when I'm thinking about my reactants, they're electron donating. Okay, so the more alkyl groups I have, the more electron donating they are. They're stabilizing the carbonyl, making it less reactive. And then when I form the product and I go from sp2 to sp3 hybridized, changing my bond angle from 120 to 109, right? Then alkyl groups over here destabilize it from a steric argument. They're just taking up more space. Right? So both of those are affecting the equilibrium. The higher, the more alkyl substituents, or the larger they are, the more they favor the reactants, and they don't help that reaction. So don't worry about any of the equilibrium discussions. This should look familiar from, Gen Chem 2, but just be familiar, right? More substituents, less favorable reaction. All right, and then your textbook also discusses, this isn't something that would be tested, right? If we're looking at acetone, for example, how do we know it goes at all if it's only going 0.2%? You can isotopically label oxygen, and then it would show up later on. You could detect that in like mass spec or the disappearance of oxygen in oxygen NMR. But don't worry about this slide too much. How about a reaction with alcohols? Yeah, this is something that I do want you to know. We're going to get some new, we've had some so far, and we've got some more products here. So know what an imine is, know what an enamine is, know what a hydrate is. And then here we've got two more. This is called a hemiacetal, and then this is called an acetal. Okay, so hemi means half of an acetal. Okay, so one OCH3, hemiacetal, two OCH3s, and acetal. And these are formed by reacting an aldehyde or a ketone with an alcohol. Alcohol still is a poor nucleophile, so it requires an acid catalyst. Okay? If we react one equivalent of the alcohol, that gives us the hemiacetal, and then if we add in a second equivalent, right, then we get the acetal. You can also sometimes see these referred to as ketals and hemiketals. So if you see that on your sapling or anywhere else, they mean the same thing. Acetal is equal to ketal. How does this work? Well, the first steps are all the same, right? Protonate my carbonyl, then the alcohol is attacking, then I deprotonate, I formed my hemiacetal. Right? And then this is an equilibrium here, two equilibria to consider because both oxygens could be protonated. I can protonate this oxygen, move back, or I can protonate this oxygen and move down. Okay. Now, if I protonate my OH, form water, leaving group, we talked about this at the beginning of the video, now I've got that lone pair that's going to jump down. Okay? That's forming an O-alkylated intermediate, basically just a ketone with an alkyl group on it. Okay? That's not stable. Notice that positive charge on oxygen. So that's why I bring in a second equivalent here, and then I deprotonate, and I form my acetal. Okay. Now, acetals, right, they shouldn't look super stable because I've got two oxygens on the same carbon. So I do have to remove water out of solution to get these things to be stable. Okay, you can isolate them, but they're not exceptionally stable. They do readily hydrolyze back to the ketone. Okay, this is how sugars are actually hydrolyzed in your body. Okay, so you've got to be on the lookout for that. Anything that's formed in this video we've been talking about can be hydrolyzed back. Okay, So not exceptionally useful in synthesis, but they are used for protecting groups, which we're going to talk about in the next video. So to summarize everything we've seen in this section with the nitrogen and the oxygen nucleophiles, right? We talked about them in order: imine, enamine, hydrates, hemiacetals, and then acetals, right? All similar mechanisms. We have that nucleophile that has a lone pair that remains on the attacking atom. Okay. We have water that gets eliminated from a protonated intermediate that gives us a positively charged species, okay? But that positively charged species doesn't hang around. It reacts to them, form a neutral product. How does it form that neutral product? Okay. If we had an imine or a hydrate, they just lose a proton directly from nitrogen or oxygen. An enamine, to form that alkene, lost a proton from the alpha carbon, okay? And then an acetal, right, adds the second equivalent of an alcohol. So that's actually not perfect. This should say a hemiacetal, adds a second equivalent of an alcohol to form the acetal. Then we lose a proton. But at the end of the day, we always have to end up with a neutral compound. So that wraps up this 16.8, 16.9. We'll pick back up in the next video with discussing protecting groups.